Hi everyone, today we will learn about a simple AI search algorithm called breadth first search. We'll code it from scratch in Java to solve a simple puzzle. The toy game we will be using is the 3-digit puzzle as defined below. So given 3-digit number called S, a start, and G, a goal, and also a set of 3-digit numbers called forbidden, we want to get from the start state S to the goal state G in the smallest number of move. So a move is defined as a transformation of one number into another number by adding or subtracting 1 to one of its digits. So for example, a move can take you from 123 to 124 by adding 1 to the last digit, or from 953 to 853 by subtracting 1 from the first digit. So that's a setup. To spice it up a bit, we're gonna add some constraint. So you cannot add to the digit 9 or subtract to the digit 0. So it's not circular. You cannot make a move that transforms the current number into one of the forbidden number. And the forbidden number can be anything. And you cannot change the same digit twice in two successive move. So this is the major constraint in this thing. So this puzzle was taken from the course Introduction to Artificial Intelligence COM 3308 from the University of Sydney. It's linked in the description. So to create our agent, we need two things. We need first the concept of a state, which defines the environment the agent is currently in, as well as the action that he can take to go from one state to another. So this thing is best represented as a state graph with arrow showing action. And now we also need the concept of a search tree, which where the root of the tree is the initial state. So in our case, the first digit number that is given to us, and each child node is a possible path in this tree. So our algorithm will be traversing and constructing this state tree dynamically to find the goal node that is also given to us. So the algorithm we'll be reviewing to search this search tree is breadth first search. So it's a classical graph/tree search algorithm. Its behavior is very simple and work kind of like this. So for a given node, do the following. So check if this node is the goal node. If yes, you just return it. Then you add if it's not the goal node, you add all of the children of this node to a queue, which is empty at first. And then you take the first element in the queue and call breadth first search on it. So it's literally 3 lines of ID that you have to do. So this is pretty much it. So what this setup will do is that it will allow us to methodically look at every layer of the search tree, one after the other. This is great if the goal node is not too far deep from the start node, but it can be prohibitively a slow search if the goal node is very deep. So in After let's look at Java implementation. You can find all of this code along with the documentation on my GitHub, which is linked in the description. Alright, so here we are. So there's basically 3 files that we need to worry about. We have this test file. So we're testing a bunch of stuff. We're testing if we can create our stuff over here. We have the setup state for all the tests. And over here, this is what really matters. It's the breadth first search. So if we look at the test before looking at the implementation, what do we have? We have this thing, a search type. We have the solution that we're looking for, right? So if we start at this start state over here, 320, and we want to get to 110, how do we do it if there's no forbidden state? So it's a simple example. So there's a bunch of ways. The most optimal way will be to do this 320, 220, 210, and then 110. So this is the optimal path for breadth first search. And to get to this, because we'll have to look at all the children, the breadth first search, we need to expand all of these nodes, right? And this is where we made this test first to test if we're good. Here we did that by hand, and then this thing will try to hit that result. So here we're using the 3-digit puzzle class over here, and it's calling the solver. We're creating the solver, and then we solve it with this search type of search, and then we just assert it So this thing supposed to work. Good, so it's working. So this is the estimated result, this is the real result. It's exactly the same thing. So that's a setup. Before diving into it, we're gonna look a bit more about a state, how we define it. So we have this state class over here. So we have a bunch of things that we want to keep track. So a state is like the environment of the game at a given point in time. So if we're playing Pac-Man, so where is the little Pac-Man in the board? How many pellets there are? Where are the ghosts? Those kind of things are the state. Here it's really more simple. It's what is the digit in this state? What was the digit that was changed to get to that state? Because remember, we cannot change a digit twice. Here we have some value, which is the backward course for another algorithm. Here, which node lead to that state, and the children of this node. And that's pretty much it. Here we also have the forbidden state that we cannot be in, but that's it. So here we have a bunch of constructor, but it doesn't really matter. You're just setting those things up. So we have some constructor for different algorithm. Here we have this main loop, which will set all the children for this node. So basically what this thing will do is it will add or subtract for each of the digit, and then it will check if this node that we just created is legit. If it's legit, it will add it to the children. If it's not, it will just not add it. So this one is easy. How do we know if a children is legit? We have to first check if this thing is in the forbidden state, right? So if it is, we're just not gonna add it because it's a not allowed state. Here, if you look, we're using Manhattan distance. It's a bit too early to talk about this, but we're gonna see it in a few moments. So basically, we're looking at the distance between this child with the forbidden state. If the distance between two nodes is the same, it means that if the distance between two nodes is 0, it means they are exactly in the same state. So they're the same. So we're checking if the node is not in the forbidden state. We check if all the digit of this new node is fine. So nothing is bigger than 9 and nothing is smaller than 0. And finally, we check if by changing this digit, did we change it twice to get to that thing. That's pretty much it for that. And finally, here we have Manhattan distance. So this is how we define if we the distance from one state to the other, and this is just looking at all the digit. So what do we do is for each digit by comparing two states, we do one digit minus the other, and we take the absolute value of this, and then we just sum this up to get the distance between the two states. So if the two digits are exactly similar in all of the three integers, this will lead to 0, basically. This also will be used as heuristic for other algorithm, but doesn't matter for breadth first search because it's an uninformed type of algorithm. Right. So this thing is just checking if the current state, this one, was already expanded before by repeatedly checking this state with all of the expanded state. If you found it, like if this is equal to one of these, then it was already expanded, so it's not expandable. Otherwise, if you didn't find it there, it's expandable. And how do you know the equality? There's two things we need to take into account. If the distance is the same, right? If the distance is the same, it means that they may be equal. But here we need two things to be the same. We need the distance to be the same, and we need the children to be the exact same digit. We can have one state which has a given digit and the other state have the same given digit, but one state could have no children and the other could have like 6 children. Even though they have the same digit, those are two different environments in the game. So we're doing a bunch of checking to see if like something is not the same in the two, some simple stuff. And after that, here we check every children to see if one children in one state is the same, is at least similar to another children in other states. And because the order can be shuffled, we have to do two for loop over here. So that's pretty much that for this. That's the state. We have all of those helper function, right? And they will make more sense when we get to the solver over here. So in this solver class, right, this is the thing, actually, this thing could be refactored a bit. The 3-digit puzzle class, this thing is absolutely useless. It's only this guy that matters. So let's look at the solver class. We're gonna stop at 1,000 iteration, right? If one of the search algorithm is too slow, we need to stop somehow. We keep track of a bunch of stuff, right? But this is to load the thing. So here, this is the constructor we saw before in the test. So we give all of this, and then we create our state over there and put them over here. So here, this search tree, it will start with the start node, and then it should end with this end state over here. So we start at the root of the search tree, and you're trying to create the search tree until we hit the end state. And when we hit the end state, this is where we're gonna reconstruct the tree, the path to the solution. So what really matters is this thing, the solve, right? So we set up a bunch of stuff. Right here we have this thing called the fringe, which is the outer limit of the tree. We do that because we don't want to construct the tree right away. It can be infinite, we don't know, and it will take a lot of memory. So you want to dynamically create it as you go instead of creating in one go. So here we need this fringe to check which state do we need to consider in the next round. So we set a bunch of stuff here. If you can look, we have a bunch of search algorithm. The one that matters is this guy, breadth first search. As soon as this thing runs and it return, we're going to have a goal state. If the goal state is null, we just return null. If it's not null, we're going to generate a solution path. We're going to generate the expanded state that we were looking at before, and then we're going to return this, which will be tested over here. So this is the solution path, and this is the expanded result that we're looking for. Good, so let's look at breadth first search now. Alright, so let's look at breadth first search. So it's super simple. If you remember the pseudocode that we had before, we have the current state, right? At the beginning it's the root state, so it's the starting state. We increment the number of iteration, and here we add this state in the expanded state because we went there, right? And here what we do is we check if the Manhattan distance between this state and the end state is the same, like 0. It means that we have to return the current state or the end state because we went to the goal, and then we don't have to continue creating the tree anymore. We just have to backtrack and we're done. Over here we check if we're there, it means that we went for a long time, and then we have to return because we didn't find the thing. Perfect. So then at a high level, what happened is we're gonna add all the children of this state to the fringe, right? So remember, the first thing the algorithm does is it check if we're done, if we're the goal state. If it's not, we're gonna add all the children to the queue, the fringe here. And then here we do something special. We're fixing the fringe because of a particularity where a children added long ago could already have been visited as we went a bit deeper in the tree. So this is a way to fix it. And finally, after that, what happened is we check if we still have something in the fringe. If not, we return null. If yes, then we get the first thing out of the queue, right? So here we pop from the start, and then we reiterate breadth first search. So it's a recursive algorithm. So the only thing we need to look at is those two functions, and then we're going to be pretty much done. Okay, so This is actually going to the fringe. It's super simple. We have this state. What do? Is we go around, right, the children of this state, and then we just check if this state is expendable. If it's not expendable, then we do nothing. If it is expendable, then we add it to the fringe. That's pretty much it. But like I said, the fringe can become stale, so we need to fix it from time to time, and we decide to fix it every time we add, every time we're checking for something. So here what we do is we iterate through the whole fringe, and then we're gonna remove something, and then if this state is still expendable, we're gonna put it here into the new fringe, and then we're gonna return. Actually, we're gonna set this fringe to the new fringe. This is a bit wasteful, right? For breadth first search, because you could just check the one that you pop and then stop as soon as you're done. But this is a useful helper function for the other search algorithm that we'll be looking at in other videos. So that's pretty much it. This is breadth first search. It's a super simple algorithm. It's an uninformed search, so it's a bit dumb. It doesn't know if it's getting near or not. You just hope that it will get near it at some point. But that's one kind of way of creating an artificial agent that will solve the puzzle. Alright, thank you for watching. I hope that this little tutorial was useful. If you have any questions, do let me know in the comments. Don't forget that you can get the code on my GitHub repository, link in the description. In the next video, we will look at another simple search algorithm using AI called depth first search. So have a great week.